Welcome to the Geological Society of the Oregon Country Meetup. We meet up every fourth Saturday of the month here on Zoom, and you can access that through our Meetup page or through our website, the Geological Society of the Oregon Country. My name is Paul Edison Lam. I'm the Communications Director. I'm just going to let real quickly our board members introduce themselves, and then we're going to jump in with some announcements about future meetups, lectures, GSA, field trips, and then we're going to have a presentation on Port Townsend from Andrew Dunning. So who is our president of this club? Raising his hand silently is Clark Woodendorf.
I'm your president for this year. And let me add just one comment. We're going to open nominations up for board members pretty soon. And so anyone who's interested in participating, even being the president, let me know. And we'll form a committee here pretty soon and start that process. And that will, the new board will probably start in March.
In March. And I would also really encourage people to think about joining the board. We have a wonderful board. We have for many years. It's just a lovely group of people. And we sort of train you along the way, help you fit into the role and find something that works for you. So it's really a lot of fun. Who is our programming director?
I'm your programming director, and I'm a past president, and so I'm the one who organizes the lectures and gets them to you. So I have a good lineup ready for all the way through February of next year. So so stay tuned, and our lectures are advertised on our website, and then an email goes out too. So we've got everything kind of in line there for that.
All right, and we'll come back to you in a moment, Sheila, to hear about all of those exciting lectures. And who is our field trip coordinator?
That would be me.
All right, who are you?
I'm Carol Hasenberg, like it
Welcome,
says
Carol.
on the thing down
like it
there.
says right below your face. Okay, and we'll be hearing more about field trips. And we might even have Stephen, I forget your last name.
I'm Steve
Minnesota.
Erickson with the Geologic Society of Minnesota, and we don't have a lot to report, but I'll give you a little bit of a talk there.
Okay, we'll come back to you in a second. So Clark, tell us about, well, I've already told you when our Zoom meetups are. They're the fourth Saturday of the month. We start at noon, we go for an hour. I've shortened the social period, so it's no longer an hour, it's more like half an hour before we start at 11:30. But that's going to continue. We're going to continue these Zoom these online meetups because they've been popular, and we're also able to have people like Andrew Dunning from Portland State Geology Department give us presentations. So that will continue. But Clark, I think we're going to be starting in person again.
Yes,
Knock wood. When will that be?
let's try doing that again. So it's going to be the third Saturday of will it be the third Saturday of the next month and on. It's going to start in September. It's going to start at 11 o'clock. And we're going to be there at, oh gosh, help me, Paul.
Woodstock.
At the Woodstock Winery and Deli.
Yes.
And we'll follow COVID protocols, of course. And we're going to, my goal is to get back to looking and holding up rocks and figuring out what they are and helping people identify different minerals, and particularly the key minerals to sort out whether this is, you know, a lava, some kind of igneous rock, sedimentary, metamorphic. So that's kind of my focus for these meetups.
That's great. I mean, that's one of the things that I really miss about the in-person is sitting around the table and people bringing rocks that are important to them or they're curious about or they've held on to for 50 years and passing them around and then having the experts weigh in and identify. So I'm really looking forward to that as well. So we'll be doing both kinds of meetups, both the online and the in-person. And Clark, what else is coming up with the GSA?
Well, GSA, the Geological Society of America's annual meeting is held here in Portland. It'll be at the Convention Center. It is from the 10th through the 13th of October. And I've kind of pushed, along with Sheila, of having a booth for for in the exhibitors hall. And this booth will be, I got help here with my granddaughter, will be two other clubs. It will be COGS, Central Oregon Geological Society in Central Oregon, and the Northwest Geological Society out of Seattle. And we'll share a booth there. It's going to be a little cramped. What we get there is we get 2 exhibitors badges and 1 free admission to the conference, and we're going to share that free admission. So those of us who would like to volunteer have an opportunity to actually listen to talks and maybe not have to pay the full admission price to get in.
And what
So
is that?
that's,
You may not know this offhand, but off the top of your head, what is the admission price if you're not a member of GSA, and what is the admission if you
For a
are?
member, it's $440 to attend this one, and it's about $400 or $500 for non-members, but we're in that ballpark. So this is a pretty, it's an opportunity to get in and look at a lot of the things going on. I particularly like looking at the poster sessions. And so you'll have an opportunity if you want to volunteer to do that at least. So please, if you're interested, let me know, and we'll get you on the list. So again, we're going to have a booth, and it'll be a good opportunity for us meaning GSOC, to showcase our club and our society to the rest of the nation.
So it sounds like we're looking for some volunteers perhaps, and
We
contact.
can always use volunteers. Never have enough. But let me know if you want, if you're interested. It'd
All right.
be great.
Any other club news before we hear Carol's report on field trips?
No, I have none.
So Carol, tell us what's happening with our field trip agenda for this summer and going
Okay.
forward.
Well, we've done 3 out of our 4 field trips, and they've turned out to be really good. And I haven't, I was asked to do a presentation on the rocks, but I can improvise plenty. I haven't gotten any photographs or anything from Clark and Sheila, and I'm hoping that somebody will write something up on that trip and get some photos together. I can help put that up on the web if we want to do that. So on the Eastern Oregon field trip, I've already put an article up on the web, and most of that was written by Bill Burgle and Emily Cahoon, and then I did some editing and added a few things to it too, and put some photos in there. So you've all hopefully have seen that. Let's just look at some rocks from that trip really quickly, and let's see, I want to do a screen share. And gosh, it's been so long since I did a screen share. Do I go under myself or, oh no, it's down here, screen share. There we go. All right. And here are those rocks right here. Can you all see the rocks?
Yeah.
Yes.
Okay. Yeah, I did some photography yesterday. So here are a couple of the rocks from that trip. We saw 2 different kinds of tuff. One was the tuff that Carrie had us looking at on day 1. That the most, of course, spectacular outcrop of that is Smith Rock, but there are other places in the Crooked River caldera that tuff occurs. And I actually got this piece. I think I had Bill snag it for me when we were driving by the outcrop in the Prineville Reservoir area. So there was a big, maybe 2 or 3 outcrops there in the Prineville Reservoir area. There was actually, as you were driving out towards the Ochoco National Forest and the Sunstone Mine, there was some rocks there too.
Carol, remind me again what this tuff is from where, and or what it's from the caldera, and what period is that? How old is that?
Oh boy, okay, the Crooked River caldera, I
Did I
believe
make it
is
much more
coming in
complicated?
at around 29 million years.
Okay.
And but this would have been a little well, I think this would have been from the main eruption of the Crooked River caldera. Carrie and Sheila will correct me if I'm wrong. So then the second tuff is a bit older. I think it's like 33 million years, the Tower Mountain caldera. And it produced this tuff here, the Tuff of Dale. And we saw a really cool contact between the Tuff of Dale below and the Picture Gorge basalt above during the field trip. I'm sure Sheila, Carrie, and Lynn can tell you how fun that was to visit. And this tuff is really, it looks powdery, but it's a lot harder than you think it is, because it's welded some. And see these little blobs in it? Those are actually like pieces of glass that, you know, from pumice that is smashed together or something. They're called fiamme in Italian. All right. So rock
Can you zoom in a little on the fiamma?
fiamme. Well, sure. I've got my little program here. And you know, I can bring the rock
my
over
internet's
here.
a little unstable.
It looks, oh, really?
How do they form?
I
Go ahead.
think Emily said that they were like pieces of pumice, which is a glass, you know, a bubbly glass. And when the tuff forms, it falls from the sky or the ignibrite or wherever it comes from. Sorry if I'm not that technically adept there. But it comes together and then it starts loading itself. And so the rocks on the bottom get smushed a lot more and they're hot, really hot. So you get little pieces of glass forming in there.
So I see 3 different colors, 3 different layers. Is that due to weathering or is that 3 separate events?
You're talking about this?
Yeah, the yellow.
This is the weathered surface of the rock. And these have been, these are 2 separate stones here. And they've been, you know, busted apart so we could see the fresh rock.
Thank you.
So the angular pieces,
yeah,
in the whitish grayish matrix, those look quite, well, they're angular. Are those just those inclusions, just the pieces that float around and the tuff descended on them and
no,
welded
it was all kind of coming out of the volcano, and some of it was more like chunks of you know, would it be plagioclase or one of those minerals? And this would be more like pure glass, silicate. And
well, that would that be, that wouldn't be obsidian, would it? Similar
well,
to
obsidian is glass there.
right.
Yeah.
Yeah, it looks like obsidian.
It's all glass. So,
It's
you know,
probably
it's, you know,
country rock at that point in time and just got shot out as broken pieces.
well, but it's glass. You know, it's shiny. It's just like obsidian. It's part of the lava. It's not country rock. Okay. Any other questions?
Right.
All right, we'll head on to the next rock. Okay, Lynn probably remembers this situation pretty well because she was having some car trouble about then. And we were kind of waiting to figure out what we were going to do in that situation. And some of the people from the trip went down into this little gully kind of thing alongside of the road and found some limestone with fossils in it. So it was kind of an amazing little deal here. I think we should at least give Lynn one of these fossils here. And
Booby
so,
prize.
you know, they're from the Jurassic, some sort of limestone from the Jurassic. And also, if any of you have one of those little pens, those little scribing pens to prepare fossils and want something to practice on, this would be some pretty good stuff. So I'm looking for a home for these little Jurassic invertebrates. You can kind of see some things that are kind of shell-like. Let me zoom in here on these rocks. There's little shells here. This is a shell. And here's some more shells. You can see that this material is just full of little shells. So, and it is Jurassic in age. It's from the Baker terrain. And so this rock has quite a few shells in it. And there's a little one along the side of this area too. So, you know, an impromptu fossil find during our trip. Okay, any questions there? This was a little bit north of Delinquent Lake. So if you want an area, but still inside the Ochoco National Forest. All right, next slide. We visited, after we got done with the big contact and the Tough of Dale, we went down to the middle fork of the John Day River, where we saw an outcrop of this material peeking through the Picture Gorge basalts and the Clarno and all that stuff that was laying on top of everything. And Emily called it as tonalite. I can't dispute that. It's, I believe, either a granodiorite or a tonalite. And
it's a quartz-rich diorite.
Okay.
Diorite that has extra quartz in it. Most diorite doesn't have as much quartz.
Okay. All right. Well, thank you, Sheila.
Yes.
So there's a picture of that. And because I had just been to the Wallowas, and picked up a couple of chunks of material from the Wallowa batholith, which is not that far away, and about the same age. You know, I think the Wallowa terrain came in before the Baker terrain. But anyway, here is a little bit of a comparison between the two. And Sheila is the white and Clark is the white stuff, plagioclase.
Yeah, I think so. A lot of
Okay.
it, but there is some quartz in the, is this the tonalite again?
This is the material from the Wallowa batholith, and it was described as a I believe a granodiorite with some tonalite. I just, you know, I looked up the descriptions of those minerals on my favorite reference, Wikipedia, and I'm going to use the general category TTG because that covers everything, just about. In these types of batholiths. All right. Anybody object to that? All right, good.
TTG stand for?
It stands for tonalite. Then there's this Norwegian word, tronhalite. Oh, I looked it up, but I can't.
Yeah,
and granodiorite.
got it.
Okay, and there's slight variations in the chemistry there. But anyway, it's a good catch-all category for us. All right, next rock. Oh, that didn't work. Okay, I've made my computer mad, so we got to wait a second here. I gave it 2 commands at once. Well, we won't have any trouble eating up the time. Oh, okay, here it is. These are the 3 little sunstones I got from the sunstone mine, and I took several pictures of them so that you can see the schiller and all that. The sample down on the bottom right has a little bit of a rosy color to it, but it's pretty clear. I just liked it because it was a pretty nice chunk of the plagioclase. And then this little piece had a lot of red color and some schiller, which you can kind of see here. And then this piece had a dark red color in the center with like lines of copper schiller that were really cool. So I'll just run through these pictures pretty quick. That's the chunk with the, it's not quite in focus, but you can see the lines of the coppery schiller.
The twinning striations.
Yeah, aren't those cool?
Yeah. very
And
cool.
then that's the other piece with the nice red color. And I was turning it in different directions. And that's the clearish piece. Now, okay, so here's another photo. You can see the coppery bands in that. And then you can see the coppery schiller in this piece. Pretty good in that photo. Okay, any questions there? All right. Now I'm going to stop the share and ask you guys, do you want me to kind of go through some of the pictures that I'm going to use for the article on the webpage from the Toledo field trip?
If you can, a little bit, Carol. I think we want to toss to Sheila at about 12:30. So
Okay,
and,
let's just
and
go
maybe
right
mention
on
some
to
of
the
the
rocks.
upcoming field trips as well.
Okay, let's just go right then to the rocks on the Toledo field trip, because you will see the other things really soon, I promise, on the website. I've been working night and day to get that article done. Okay, behind me is the Umpqua River that we were just walking on. It's pretty cool because it was, you know, water covered all these rocks in the spring, and I'm going to be putting pictures of that up. As we drove towards the site in Elkton where we met, we passed this quarry, and it's a place there where there's a fold in the stratigraphy in the Tyee Basin, and instead of the Tyee there, the underlying Silesia basalt peeks through. So we snuck over there to the kind of the entry of the quarry and picked up a few rocks. And so we would have samples to show people on the field trip. And these are the rocks we picked up. And these white ones, Clark told me were zeolites that were in some of the rock we saw there. And then you can kind of see that some of those rocks have been altered. Okay. Then we went into the river, and on the thing you'll see on the web, you'll see where there were like little scour holes all in the rocks in the river. And in a lot of those scour holes, we found basalt rocks because some of the Silesia rocks are eroding out of the places where that is outcropping. And this was a really nice piece of basalt that had eroded a round hole in the Whitby Formation sandstone rocks. The basalt is perfect for this because it's a little harder than the Whitby sandstone. And I like this rock because it looked like a foot. I thought it was kind of cool. So anyway, that's that rock. The next one is actual pieces of the Whitby sandstone from the Umpqua River. And one of the characteristics that people use to describe the Whitby sandstone and differentiate it from other places is the mica crystals in it. And I think you can see those in this photograph. Okay.
Yeah. Nice.
Okay. And then this little piece over here was even more micaceous. And, it was quite sparkly on the top. I think Sheila found that, didn't you, Sheila?
Possibly. Yeah.
Yeah. And then I just picked up another little chunk of basalt that I thought made a nice little worry stone kind of a thing. But there were some interesting things going on in the river there. So we had we stayed there for a while looking at that. And the next rock, okay. Then I didn't pick up any samples in the, the state parks there for the Whitby Formation. And I'll let the pictures speak for themselves in the web article that is shortly going to be up. But the last day of the trip, Frank Flodkey took us to Black Lock Point and was really spectacular. So if you ever have a chance to go out to Black Lock Point, it's definitely worth the 1 mile hike out there to the top of the bluff. And then you just walk down the bluff and there's all these amazing rocks on the shore. So here's some samples of some of the rocks that you see. This is a black, shiny, greasy rock. Can anyone tell me what that is?
Blue schist?
No, you're not used to seeing it black.
Asbestos or talc?
No, it's serpentinite.
Oh, of course.
Okay.
Yeah, it's serpentinite. All the rocks at Black Lock Point have to do with the subduction zone that was there, which is now 30 miles offshore. But the subduction zone has been cranking along for millions of years. And so it's left this huge accretionary wedge, and some of the products spit back up to the surface. And one of these is blue schist. And here's a couple samples of blue schist. And then this, I have a better picture with labels and everything, is pieces of the radiolarian chert that is also mixed in with all these rocks. Like you'll see a big boulder and it'll have all these different kinds of rocks, and they'll be all folded and mushed and stuff because, they were put through the meat grinder. But that was a really, really spectacular point to go and see. Any questions there?
Thank you, Carol.
All right.
Very quickly, are there any field trips you want to call out that are coming up?
Well, we're going to be talking about the subject of the next field trip, and that's coming up in the third weekend in September, like the 17th through the 19th or 20th, something like that. And all the details are on the website. So there may be a spot or two left on that trip. And if you want to go, now's the time to sign up.
Okay, well, this will whet people's appetites if there is that possibility. I'm looking to see whether Andrew has showed up yet or not. I did promise Stephen out there in Minnesota that he could have a moment to tell us what kind of field trips they're doing out there. And we're a little short on time, but Stephen, we do want to hear what you're doing.
I'll keep it short. We haven't done many field trips this year because of the COVID situation, but we did do one, Building Stones of St. Paul. We're looking at some of the architecture and building stones. And what they did was they did it in the cars, and they did it as a Zoom meeting in the cars. And so they drove around and saw the buildings that they wanted to see from the cars. They had like 10 or 15 cars. They kind of limited the number of cars, so you can't have too long of a caravan. And the field trip guide sat in one car and gave the description and kind of showed it. We pointed out the window and kind of kept it that way. So it was
Wow.
not something we planned on doing, but it was that. We've
Well,
had
I'm glad
other
I
field
asked that.
trips.
We do a downtown field trip. For many decades. So people stayed in their cars and they
Yeah,
just
I guess
looked
so.
at the
I
building.
didn't get a chance to go on it myself, but I think they
city
ran it
was
as a
this?
Zoom meeting.
Maybe
Which
we'll
city,
try.
where was this, Stephen?
It was in downtown St. Paul and one portion of western St. Paul. There's some older buildings with particular building stones that were used. Platteville limestone, redstone from the Bayfield, Wisconsin area, some of these other places like that. So they were kind of looking at both kind of an architectural history of St. Paul and building stone. I also
So sorry to
do
go
a
down this
field
rabbit
trip.
hole, but so there was a Zoom meeting based on a leader who had a camera and walked up to the buildings,
Well,
or
no,
just from the window of the
she was-
cars? Or
She was just talking, and they would drive past the location, and she, through the Zoom, would say, okay, here's this building over here on the side, and describe it from that. And nobody had to get out of their cars.
the people are attending the Zoom meeting from their cars.
Yes,
Wow, that just kind of blew my mind there.
Worked.
Okay.
So
Wow.
that's kind of a weird thing. We often try to go up to Canada, but Canada border has been closed now. They just opened it up. And some of the other trips that we have tried to do in the past have been kind of closed down for the past year. So we really haven't been as active as we normally do. We always like to take about a 2-week trip out west someplace. And I would like to eventually tie in with you guys. So maybe send a group of Minnesotans out to Oregon for some reason, but maybe not this particular summer is too late. Maybe next, maybe too soon too. But in the future, it'd be great to be able to link up that way. I'll let you
Great.
get back to the meeting then. How's that?
All right. Thank you so much, Stephen. Well, Sheila, tell us what's coming up next with our lectures.
No, okay, well, our next lecture in September will be Dr. Bill Orr, and he is going to talk about 20 scientists. And he's going to talk about people that he knew personally that were influential in his career, but it's also going to end up being a history of the science of geology. So, so we got that coming up. In October, we have Andrew Meggs and from OSU, and he's going to talk to us about basin and range. And then in November, we have Josh Roaring from University of Oregon, and he is going to talk to us about some of the uses of LIDAR, which is very exciting, and finding landslides and so forth. So that's what we've got coming up the next 3 months. And we are hoping in that time to transition to an in-person meeting at PSU, but we're going to make it a hybrid because we don't want to leave out all our wonderful friends from afar that have joined us via Zoom. And so we want to have an in-person meeting and combine that with a Zoom meeting, and so that everybody can attend. So that's what we got. We got definitely some things to work out, and that won't happen until October. Also want to mention in October, Andrew Meggs is going to talk, but because of the GSA conference, we're going to push off his talk until October 22nd. Otherwise, it's the normal second Friday of the month. But for October, we're veering away from that because of the GSA conference.
Okay, and Sheila, I know you're going down to the AWG conference in California to be looking at the north end of the San Andreas Fault. So you've been thinking about fault systems, and do you have a demonstration for us about fault systems and pull apart basins that you could show us perhaps?
I've been playing around with these paper models, so I kind of wanted to get a chance to share with you some things. And so I'll go ahead. You want me to launch into it right now?
Please do. Please do.
Okay, I'm going to share my screen here. and show you California. Okay, so you can.
That's where I am.
Yeah, that's
Yep.
wherever.
It's right there.
Okay.
Yep.
So what I wanted to draw your attention to is this little area here. This is Santa Barbara. I lived in Santa Barbara in the 70s, so I'm familiar with this area. And I also, what I want to talk about here is how geology affects the geography. Okay, so this is an interesting little part of California because you think of California as a sunshine state and you go to the west to see the sunset over the ocean. But when you're in Santa Barbara, the sun doesn't set over the ocean
No.
because the ocean is to the south of you. And I always thought that was interesting before I was a geologist, but why do we have this? Well, I have an animation here, a paper model that was given to me by Tanya Atwater. And Tanya is a professor. Well, for those of you who don't know, Tanya is a very celebrated pioneer in plate tectonics. And so, and she also spent her career teaching at UCSB. So she put together this model and gave it to me and made me promise I would use it. So you guys are my recipients of that. Let me stop sharing and go to my document camera where I have it set up. Okay, and I'm gonna put myself on speaker view so I can see what I'm doing here. Okay, so I think you can see here that I've got a model. And this is a model that Tanya made.
Are other people seeing the shared screen? Because I'm not. Is it me?
No, actually what I'm doing now is I'm under the document camera. So if you put me on speaker view,
Okay, thank you.
then then it'll be much bigger. Okay, are you seeing it now?
Got it. Yeah, thanks.
Yes.
Okay, yeah, put me on speaker view for this, because I'll be doing stuff under the document camera, because this is all playing around with paper models. And this is a model that Tanya put together. And it's showing a simulation of how Southern California evolved during with the motion of the San Andreas Fault. So I'm sure everybody's kind of familiar with the San Andreas Fault. But let's talk just for a minute about the San Andreas Fault. I'll take this off and turn on the light here. Okay. So the San Andreas Fault is what we call a strike slip fault. So the motion is this way, two plates sliding past each other. Okay, the San Andreas Fault happens to be a right lateral strike fault, which means if you're standing here and looking across the fault, the piece on the other side appears to be moving to the right. Okay, so that differentiates it from a left lateral strike slip fault, which would be motion this way. Okay, so it's motion this way. Okay, Los Angeles is on a little sliver of the Pacific plate, which is moving relative to the North American plate in this direction. Okay, so it's getting closer to San Francisco, which is on the North American plate. And Los Angeles is getting closer to San Francisco every day. So they're talking about spending billions of dollars putting in a rail system. They just have to wait a few million years. It's coming up there anyway. Okay, so so here's this animation then, or this paper model that Tanya put together. And let's see, let me turn this light off. Okay, just so the glare isn't on it. Okay, so this is from 18 million years ago. 18 million years ago, the California coast looked something like this. So basically, we didn't have that piece going to the south that's making Santa Barbara. We had a peninsula here. We had the beginnings of Baja California, and you can see the San Andreas Fault here. Okay, so if I move this and watch the time here, let's see. You can see what it's doing. 12 million years ago, it was out there. It's turning. Okay, the motion of the San Andreas Fault is pulling it up there to 6 million years ago. And now you can see California take shape.
Wow.
And now you can see that extension of California where the ocean is to the south, and this is the Santa Barbara area.
So Sheila, as you know, I'm in the San Fernando Valley in my parents' home in Northridge. Am I, it looks like I'm about where the rotation point is, where the grommet is on your diagram. Is that, do you happen to know if most of the Los Angeles Basin is part of that transverse?
Yeah. The Los Angeles Basin has several different faults cross-cutting it. But you do have the influence of the San Andreas Fault there, but the whole basin has got other faults too as well. And so it kind of takes up, it kind of mitigates the action of the San Andreas Fault by having a bunch of little pieces there that can move in different ways. And so that kind of mitigates the real hard effects of the San Andreas Fault.
I notice here, which I didn't notice when I was a kid, but all of the strata in the mountains to the west of us they're all pointing. They're all tilted down to the southwest and up toward the northeast. Is that part of that rotation, or is the Pacific Plate sort of pushing it all up? Or yeah, do you know how that works?
Well, there's a lot of different, it's complicated, and there's a lot of different things going on there. You've got the transverse range, which is of the mountain ranges that run east-west, and they're described as an echelon faulting, which has to do with the strike-slip motion, but little areas in between get squeezed, and so that's why you get those east-west mountains. So again, I just want to demonstrate. I'll just do this demo one more time, just so you could see without the explanation. So we're 18 million years ago. And then
18 million years ago was when the fault started.
That's what the initiation. The volcanism that was going on in the Sierra Nevada shut off at that point, okay, because the Superlon plate was subducting under it, and then it goes to a transverse fault situation.
Oh, I didn't realize it was that recent.
Yeah.
And so the San Andreas Fault is 18 million years old, or that system?
Yeah, well,
Okay.
that's, that's what she thinks that it initiated. Okay, so I just wanted to, she was very kind to give this to me, and I don't use it too much in classes, but I wanted to give you a chance to see it.
That's
Okay.
pretty cool. Thank you.
Now, let's talk about
Lynn?
Oregon here for a minute.
Lynn, do you have a question?
Yeah, what is the continental borderland that's kind of marked in the different color blue, more of a purpley blue? Is that continental plate that's been transferred over to the Pacific plate and moved along?
I don't know what I think she meant that was the continental shelf.
Okay.
Yeah.
Because it kind of moves with it, so it's a little tricky.
Yeah. Okay, then I wanted to talk to you about Oregon. So let's talk about Oregon. It has long been noted in Oregon. I got another paper model here. And this is showing Oregon, okay? And it's showing the magnetics in the Coast Range. So the Coast Range, the Silesia block is made out of lava that cooled, and as some of you might know, when lava cools, it's got magnetite crystals in it that orient themselves and can turn and orient themselves the direction of the magnetic field of the Earth, which was pointing to the north at this time. But we see now, it's long been noted that we see those arrows now, instead of pointing directly to the north, they're cocked over a little bit. Okay, so there's been lots of different explanations for why the magnetics in the Coast Range are all tilted. And the basic idea is that Oregon is rotating in a clockwise manner. So if I put Oregon on here like this, and let me get situated here with, okay. We can see that Oregon is basically moving in this direction. Okay. The whole thing is rotating. This part of Oregon is rotating clockwise around a center point in Pendleton. Okay, so that clockwise rotation means that we have a lot of different things going on. One thing we see in Oregon is we see a series of strike slip faults that run in this direction. The Eugene Denial Fault is one. Okay, there's another fault down here. And the ones I want to call your attention to in the Portland area make up the Portland Hills. And there's also the Gales Creek Fault that runs from Gales Creek to Mount Angel. They're all basically parallel. You see all these faults running through Oregon, and they're all oriented the same direction, and they're basically parallel to each other. If I take a piece of cloth here, I can demonstrate what's going on with a piece of cloth here. Put down a piece of cloth. Let's see, turn on the light for this so you can see this, okay? And if Oregon is rotating in a clockwise fashion, I'm going to use my hands as a demonstration, and I'm going to show you when you rotate, guess what you get? Can you see those wrinkles there?
Oh, yeah.
Going that way. So that's basically the explanation that we have for all those strike slip faults that run in that orientation. Okay, so what's that doing in the Portland Basin? The Portland Basin is what we call a pull-apart basin. I'm going to get a book here, a map, to kind of show that. Let me turn the light on here. Okay, so here I've got a landform map that is showing the Portland area. We've got the Portland Basin right here. We've got the Portland Hills that run right through here. So that's a fault. Okay, and then what we have here is a fault that's offset, the Oregon City Fault that runs through here. Okay, so I am going to put my pieces of paper on here. I'm going to put the Portland Hills Fault right here and line this up. Okay. And let's make sure Oregon City is right here. So I need to be right about there. Okay. So basically we have the Portland Hills Fault running in that, trending to the northwest. We have the Oregon City Fault, which is also running in that direction, but it's offset a little bit. And they're kind of broken in between. I'm going to zoom out just a little bit so you can see a little bit more. Okay, the motion is still the same. It's still a strike slip motion. Okay, so that means that this piece is moving this direction relative to this one. It's moving that direction. But what happens when they're offset from each other and I pull them apart. Notice the area in the middle, the pull apart basin. And that gives us the Portland Basin. So this is what we call a pull apart basin. It's the action of two strike slip faults that are offset from each other a little bit, but they're doing the same motion, the strike slip motion, right lateral strike slip motion, and you end up with a low spot.
Sheila, I'm remembering that there are 4 pull-apart basins that are sort of clustered in that part of Western Oregon. Or do I have that correct?
I don't know. I don't know on that. Somebody else can maybe chime in if they do.
Maybe Matt
I
or-
don't know the particulars of the Portland area that well, but
Because I think the Tualatin Basin is another.
there's obviously, I'm giving you a simplified version,
Mhm.
but nature is always way more complex. But anyway,
I know Matt Bernengo, it might be with us, and he's worked on the Johnson Creek watershed tour in the.
yeah, somebody
We've
who's
talked
worked in
about
that
that.
area wants to chime in. I also think it's.
Matt's kind of shy, so he might not want to pipe up. I don't know if he's still with
I
us.
also think it's interesting that the boring volcanics, which are much more recent.
Well, exactly.
are coming up in that area.
Yeah.
Okay, so is it that we dropped down and we allowed that magma that was pooling under there to come up? I don't know. I don't
Well,
know. 'Cause I
I'm
haven't worked-
equally fascinated by that because those boring volcanics, if people have been on those field trips or heard us talk about that, most of those buttes are also, I guess they're hoarse. They're surrounded by normal faults and they are part of that pattern of uplift. But it's more complex than I can understand it at first blush. Matt, are
Yeah.
you there? I'm wondering if Matt. I'm trying to draw him out here, but yeah, absolutely.
I've hardly ever been described as shy before.
Yeah.
Hi, Matt. Good to
Hi,
see you.
Sheila. Yeah, I mean, to your first comment, Paul, yeah, I think Tualatin Basin and Northern Willamette Valley, south of the Portland Basin, also qualify for these sorts of things. Yeah, and so extension was, I guess, in the eastern boring hills over towards Damascus and the foothills. I think a lot of those surprisingly were well, to me at the time, mapped as horse and grabens, uplifts and down drops. So normal, extensional normal faulting sorts of things. And extension is what probably let the boring magmas get to the surface through the Portland Basin.
So were they horse first and then volcano second? Or some kind of
Well,
combination?
if you've got magma under there, and if you crack the surface and you put pressure, stretch it thin and crack it, you allow that stuff to come up through it.
Yeah.
It wants to rise, but it needs a conduit sometimes to get to the surface.
Yeah, some of one, some of the other, some mixed. Remember, we kept wondering about Pal Butte. I guess it was that
Right.
the lava came at the base, not out of the top or something like that.
Yeah, those Pal Butte and Mount Tabor have river rock on the top of them. They have
Yes.
either Troutdale or Springwater River Rock, and the volcanics are, at least those left by the Missoula floods, which have probably eroded a lot. The volcanics are all on the northeast side.
Yeah.
So it's kind of fascinating. It's fascinating too to find volcanics that have the river rock embedded in it.
Yes.
I think, do we have any idea? I mean, the pull apart basin Tualatin in Portland has been going on for a million years, tens of millions of years, but the volcanics are only, at least we can see, are only a couple million years. 2.6 or whatever is the oldest boring. So the boring phenomena is more recent than the pull apart basin by an order of magnitude.
Yeah.
Yes. Yeah. The faulting in the Portland Basin affected the Columbia River basalt flows in either damming them or channeling them or something like that. So obviously those had to be going on more 12 million years or more before that. And right, the oldest borings are 2.5 or 3 million. So there's a bit of a gap there.
It's a mystery.
Good.
Well, thank you, Sheila. Seeing it in paper and fabric really kind of makes it a lot clearer, sort of how the mechanics work.
Yeah, that's why I wanted to do it.
The basic physics is sometimes a little hard to understand from just the diagrams.
Yeah.
It looks like Andrew's not going to be able to make it today, so
No,
I think we'll.
Andrew's with us.
Oh, is he with us?
Yeah,
Okay.
hi,
I just got
Andrew.
here.
All right. We're just about at our hour. I'm not sure if we want to push Andrew's presentation over. I know there's some people who want to talk about Port Townsend, so I'm happy to go a little long, but I'm going to sort of throw it out to the other people on the board here. Andrew, do you want to talk about this next month, or?
It does say 1:30 on the website.
It does? Okay. Well,
Go for it.
that's
on.
my area. Okay, well, people want to hear from you, so I will. We will. Someone should introduce Andrew. He's our master's student friend and collaborator from the Portland State Geology Department, and a wonderful video producer. Andrew, take it away. It looks like
Hi. So I just got back last night from my final research trip for the summer for my master's degree. Scott, I collected a lot of bags of soil for you. So they'll appear in S9 one of these days. Found some really interesting stuff. That's very exciting. I'm studying a fault history out in Eastern Oregon in the Strawberry Mountains. And for recreation, I went up to Port Townsend couple months ago and made a video about the interesting geology up there. It's on YouTube. Paul asked me to share it. I guess I can do that. I can just sort of broadcast it to everybody, and I'll put the link in the description. Is that still? Do you still want me to do that?
Do I? Andrew, what do you think? If you're able to extemporize without the video, but I'll leave that up to you. Whatever you feel like works for your presentation best.
All right.
And for those of you, we usually stop at the hour. We're going to go a little long. Andrew's content is worth it. And the conversation about Port Townsend, drop off if you need to. This is our hour. But I think there's a lot of people who want to hear about Port Townsend, and it's pretty fascinating. And since I can't go on the field trip, I want to hear about it. Why don't you share the video?
The whole video? It's like 8 minutes. Seeing a lot of head nods.
Yes.
All righty. Give me just 1 second. I'll pull that up.
I think, does Carol Hassenberg happen to have it already?
I do. I happen to have it in the queue. Shall I share?
Yeah, go
sure.
ahead.
All right, where did I put it?
See, we've got our production down, Andrew. We're on top of this.
Well, we hope so. Let's see. It's something to do with my Google Chrome. That's the wrong thing. Let me get it up on Google.
I've actually got it up right now.
Oh, okay. There you go.
Didn't take long.
Oh. Okay. Share.
Oh, there we go.
Yeah, that's me. Oh, I got to hit the button. Duh.
We can't hear. Share this computer sound when you share your screen.
Can you hear it now?
No.
It's very quiet.
All right.
Stop.
The problem is that I'm not sharing my computer sound.
Right. And there's a little checkbox on the left when you go to screen sharing.
Oh, okay.
So you have to stop sharing.
Stop share. Button on the left.
Little lower left. There'll be a little checkbox.
Okay, share sound. Got it.
Okay.
Share.
50 million years to the Eocene period. Back in ancient times, its geologic story is most dominated by glaciers. But the basement rocks far below go back as far as 50 million years to the Eocene period. Back in ancient times, this part of Washington was part of a large island called Silesia. As the oceanic plate subducted below North America, Silesia became accreted and stuck onto North America, and that's how this part of Washington was created. Very few rocks remain from the Eocene to more recent times, but the rocks we do have are mostly related to glaciation. During the Pleistocene period, which began 2.6 million years ago and lasted until about 10,000 years ago, this area was repeatedly covered by large glaciers. The Cordilleran ice sheet extended south from the Rocky Mountains and the coastal ranges of Canada, and numerous times over that 2 million years this area was buried by ice. The most recent period of glaciation is called the Vashon Advance, and this Vashon stage of glaciation began about 18.6 thousand years ago. This Vashon Glacier was as much as 4,000 feet thick here at Port Townsend, and it deposited glacial debris called till. A lot of the rocks in this glacial till came from as far away as northern British Columbia, hundreds of miles to the north. Most of the Port Townsend area is covered in what's called a lodgement till. Now this is glacial deposits and debris that is buried below the glacier, and since it's a huge stack and a large weight of ice pressing down on the sediment, it gets squished and pulled apart and crushed into what is called a lodgement till. Areas are also covered by an ablation till or a meltout till, which is created by when the glacier retreats and melts, and it reworks a lot of the sediment and leaves behind other rocks and gravel and debris, which is then moved around by the water, and this is called an ablation till. So here at North Beach, which is along the Strait of Juan de Fuca on the north side of Port Townsend, we have a very interesting contact. On the bottom here is glacial till, and above it is marine sediments. This is called the Everson Formation, and it was formed at a time when this area was underwater. So after the glaciers retreated and melted, Port Townsend and the rest of the Quimper Peninsula was underwater. This line between them, separating the marine sediments and the glacial till below, is called a contact. And a contact is a plane between two distinct geologic units. So this unit below is not just a glacial till, it's what's called a glacial-marine deposit. So after the glacier had melted, or was at least stagnated, the deposits and the gravel caught up in the glacier and below it were getting worked by the ocean, by waves and in shallow water. In certain areas on North Beach, you can see fantastic crossbedding and other indicators of current and marine action. Let's go see some other examples of this type of material. One of the key indicators of glacial or glacially derived sediment is the wide variety of rock sizes. So here we have sand ranging from fine sand to coarse sand, but most strikingly is this large block. Now this large block is, it appears to be some kind of marine-derived mudstone, but it's surrounded by all of this nice, finely laminated, water-deposited sediment. So some of the structures I've seen in this outcrop indicate that the main currents were flowing east to west. And one of those indicators is these cross beds I see here and here, where it's sloping a little bit. There's better exposures elsewhere on this cliff. But this big block here suggests to me that it fell out of an iceberg. So when a glacier is moving across the landscape, it will pick up rocks and boulders off of the landscape, and sometimes these get trapped in icebergs. So when the glacier is melting out, and this is all underwater, this is all deposited in water, icebergs floating around and rocks that are trapped in the iceberg fall out. This is called a glacial drop stone. You can see how soft it is compared to some of the surrounding material. And so large drop stones such as this are indications of a glacial or near glacial environment. Here you can see examples of some of these cross beds. A cross bed is a feature that indicates moving water. So when water is moving, in this case from left to right, it's depositing sand and gravel in sequential angled layers. And these are indications of what we call paleocurrent, or what direction water was flowing when these sediments were being deposited. These sediments were being deposited probably around 12,000 years ago as the Vashon stage was ending. You can also see evidence of some of these diamictite glacial drop stones, like this one here. There's a few others elsewhere in the wall. Further evidence that the glacier was retreating and melting at this time. So the further east you go on North Beach, sort of between the parking lot for North Beach and Point Wilson, you get into a section of the cliffs that are very tall, and this is called the Whitby Formation. These cliffs are very different from a lot of the other sedimentary rocks we see in Port Townsend, and they're actually the same rocks that are visible in the cliffs of Whidbey Island across the Strait of Juan de Fuca. These rocks indicate sort of a floodplain environment. It's all very fine sand with lots of that same cross-bedding and laminations and other layers that indicate periods of flooding versus areas of river erosion and river processes. So one of the cool things about North Beach is that all of the larger rocks that came out of the glacial sediments are sort of jumbled together here on the beach. And this here is a great example of a rock that was brought in on a glacier. So this is stolen, imported Canadian rock. This is a granite, and most of the granites we see in the sedimentary rocks around Port Townsend come from the British Columbia coast ranges, several hundred miles to the north. And so this rock is, in a way, a reminder of just how large these glaciers were, by bringing rock all the way from the coast ranges of British Columbia down here to coastal Washington. So since the higher parts of Port Townsend are all this soft glacial sediment, that makes them highly susceptible to landslides. The cliffs all along the northern end of Port Townsend meet the ocean, so winter storms will drive ocean waves into the soft rock, which causes landslides, such as the one that closed this part of Cook Avenue some years ago, causing the road to slide into the ocean. So this huge weight of ice that we've been talking about, the Vashon Glacier, and the many other glaciers that preceded it, pressed down on the crust of the Earth and displaces the mantle below. The mantle rock actually flows in a solid state away from this mass of ice. And now that the glacier has melted and disappeared away, this area is slowly uplifting as that mantle rock flows back to fill the space. This is called post-glacial rebound. And this whole Port Townsend area was underwater until about 12,600 years ago, when the glacial rebound caused it to re-uplift and reach the surface. Here in downtown Port Townsend, the historic downtown area is built on artificial fill. So when this port city was growing and expanding in the late 1800s, the marshlands and beaches were simply filled out into the ocean to create room for the bustling port city. So that concludes the geologic story of Port Townsend. This has been Better Geology. I'm Andrew Dunning. Thank you very much for watching.
Thanks, Andrew.
So Andrew, tell us about making the video, and also if there's anything you'd want to add. And I think there's some other people who have some interest in the Port Townsend field trip that's upcoming.
Yeah, so I generally try to make a video when I go somewhere, depending on where I'm going and what kind of time I have. And I knew there was going to be primarily glacials related stuff, which I haven't done too much of on my YouTube channel, so I thought it'd be a good addition to my existing material. So I looked at, the first thing I looked at was the geologic map for the area published by the USGS. I think there's also one from the Washington State Geological Survey. But I looked at that, and what I found was very interesting, and that's basically what you heard in the video, was that there's a wonderful sequence of both glacial till and sediments, and then sediments related to the retreat of those glaciers and modification thereof. There were a couple of things that, that exposure at North Beach, which is along just the northern coast of the Port Townsend sort of city limits, is really interesting. And it wasn't until after I got back from the trip I was able to find some good information on that. And what I had interpreted as glacial drop stones was in fact probably giant rip-up clasts. Actually, I have a good picture of that handy. Let me screen share that.
Yeah, explain that.
Yeah. Sorry, I gotta get rid of the kitty here. Let me pull that up. So that whole, a lot of that when I was looking at the cliff there was actually just me interpreting what I was able to find in the outcrop, because I wasn't able to find too much pre-existing writing on it. Here we go. So this outcrop here, I didn't include in the video because it was a bit too visually. And so there's a lot going on here. So we have these big blocks here, which is of a glacial, post-glacial mudstone, so probably standing water. It's generally pretty fine. It's mostly mud. But there's all of these huge blocks of it. There's actually an outcrop just off to the right of the image frame here. And you can see all the cross beds here and some of these laminations. So this is after the glacier had retreated from this area. There were these strong meltwater currents flowing from east to west. And because this rock here, the brown sort of marine-ish mudstone, is really soft, these currents were quite literally ripping chunks off of the outcrop and laying them down in this conglomerate sandstone to the relative downstream of these outcrops, which is actually way cooler than what I said they were in the video. But ultimately, I didn't have enough time or energy to do voiceover and re-edit all of that with video footage I didn't actually have. So I left it the way it was, and I'll augment the description a little bit to reflect that. And I actually got some email from the Quimper Geological Society, who you'll be collaborating with on the field trip. Unfortunately, I won't be able to attend, Carol. If I hadn't gotten back from my field research trip yesterday, I would have contributed more to that email thread you were all talking about. But there's a lot of very, very interesting outcrops here. Look at the size of these cross beds. These are about these 2 to 3 meters in height, these cross beds, and they're really low angle. A lot of absolutely stunning structures in here. This is that big block. This is a different.
Andrew, explain for people what cross beds tell you about the direction of the flow.
Yeah, so when you have water flowing, sediment is moving along the base of the water column, and it tends to deposit new sediment. If you're looking at the base of a creek and you see ripples migrating along the base of the water column, these are those, but sort of lithified and preserved, and you see a cross section of it, and you get these diagonal beds of material that progress downstream of the water flow. So here, this shows us that the water was moving from left to right on the image, which correlates to east to west, because this is pretty much facing due south from the beach. Let's see what else. So here's that big block. You can see the conglomerate on this side, which is, as this would have been ponded behind this big block because the water is moving from this side to this side. There's some cross beds over here that you can't see super well in this image. But this is cut down into these pre-existing laminations here. A lot of the structures here are, they're difficult to photograph because they're large scale, but all of the features are small scale. So if you back up to the water and you take a picture of it, then a lot of it doesn't come across very well. But you can see these laminations here, which reflects a lot of water moving, probably pretty thin. Not quite thick enough to leave cross beds behind, but there's a lot going on here. Look at the size of some of these rocks. The laminations are just beautiful. Very soft rock. Not lithified really at all. Well, that's a piece of art at the downtown museum. Oh, found a clam. I used to come to Port Townsend a lot as a kid, because my grandfather had moved up there later in his life. So I was able to visit a lot of these places without any knowledge or appreciation of the complex story that they tell. But going back now as a geologist, it's much more interesting. And I'm sure there'll be some real glacial experts there on your field trip that'll be able to tell you a lot more detail about these outcrops. There's a lot going on there. You can see, really understand the whole progression. So that Whitby Formation that I mentioned in the video is actually the oldest exposed interglacial period. So that's an area of sort of floodplain activity, but there were no glaciers covering that area. So all of those rocks predate the most recent glacial advance. Those are actually older than a lot of the glacial sediments. Really cool stuff.
Wow.
A lot of detail can be
Yeah.
defined.
I-
Questions, comments?
I can throw in a plug for this trip, or several plugs. Kitty Reed is a friend and former coworker at Washington Division of Geology, who retired up to there, and Mike Bichette, I think, retired from California. There's a thing about retiring in the Northeast Olympics and at San Juan Islands, because it's like the banana belt of Western Washington. They both know a whole lot about that area. That corner of the Olympics, as Andrew said, all kinds of things. The glaciers come, the glaciers go, the sea comes in, the sea goes out. There's a wonderful story there. And it looks like you're staying at Fort Warden, which was, some of you may know and some not, the site of the filming of An Officer and a Gentleman, even though the place had nothing to do with training Navy pilots. But it was a major coast artillery station guarding the entrance to Puget Sound, along with a couple of other places. I've never been to Fort Flagler. Fort Casey on the west side of Whidbey Island is pretty much gone because it's eroded into the sea. But it's a great place to stay. The old, late 1800s through mid 1900s quarters on the base are very well preserved, and the geology is really pretty cool too. So how can you go wrong?
And Carol, we do still have openings for that field trip?
Yes, I think there may be an opening or two left. The trip is filling up though, so. We actually have someone here listening that is trying to register, and I have to register her after we're done with the meeting. Okay.
Andrew, I have a question.
Yeah.
So that Canadian granite that you found on the beach, North Beach, was it?
Yeah.
So part of it looked like it was smooth, the central part. And when you first said it was a granite, and I was looking at it, that looks like a basalt. I could tell the granite on the upper and lower portions. Why was the second video? Why did it seem so smooth?
So the whole rock was actually very smooth. It was completely polished both by glacial action and just from being in the surf, really is where it is. We were there at low tide, so normally that's underwater. But that was a big, it's actually a granodiorite, and it contained what's called a mafic enclave, which is, if you think of like a granitic body of magma as mostly homogeneous, it's not truly homogeneous, but it's getting fed from below by melt from the mantle or lower crustal melting, whatever is feeding that magma body. It's going to be more mafic, more basaltic in composition. So you'll occasionally get these globs of basaltic melts surrounded within the rest of the granite. And that's exactly what that was. I didn't want to, I did start to talk about that in the video, but I decided that's not really relevant, and I cut it out for time because the video was already quite long compared to what I normally do.
Okay, thanks.
That's a very, very astute observation.
Any other questions, comments? Any rags, any bones, any bottles today? I want to, we're past our time. I like to wrap up in an hour. Andrew's right. The website did used to say that we went till 1:30. With the recorded time though, I like to keep it under an hour. I have to say though, that today, Carol and Sheila and Andrew, this is exactly the kind of content that I think people want to come for, and the kind of conversation that we can have that's not quite as possible in the bigger lectures, or even in person. It's a little easier, and we can have people like Carrie and Stephen joining us from afar. And so thank you, all three of you, so much for your contributions today. I'm going to turn off the recording with the button that I find on my screen here somewhere. Where's the button? Nobody talk until I find the button. There it is.